So, hi and welcome everybody to the lecture titled OFDM and its simulation using Matlab software. So, everybody got this book that I have shared with him previously, and I asked you to go over it and check the material related to OFDM and especially the simulation part of it. But I have learned that some of you are facing some problems, and this lecture is basically to address these problems, to teach you OFDM simulation, the transmitter design, the receiver design, and the channel parameters, and the meaning of each parameter, and what and to get the bit error rate, and if it's possible the throughput as well, and understand the general structure of OFDM simulation. After that, we are going to propose some ideas related to improving the performance of OFDM furthermore, especially in the context of 5G, and then try to put these ideas and simulate them. You take these ideas with you at home after the lecture and you try to execute them, simulate them, and get reliable results. And then, of course, these ideas are going to be novel, on the state of the art, not something that's repetition from the internet or from other sources or other papers available on the literature. So these are the main objectives of this tutorial, kind of. And after that, I will give you overview about how to write a patent, because since your ideas are going to be novel, so we are going to talk about the main parts of filing a patent so that you protect your work and the idea. As you know, I'm going to be the partner of each one of you, and I'm going to distribute the ideas based on your capabilities and your skills and your commitment. The ones who are better committed, the ones who work hard, the ones who are willing to work on the idea even after the semester finishes, I'm gonna continue working with them until the idea is being patented, and then hopefully after that licensed to some big companies. And you will get your share, of course. I will teach you other ways of course, of how you can make money out of how you can make something of value out of your work and out of your contribution. So this is basically what we are going to do, and I hope you will focus and follow me in this lecture step by step, and make sure you don't miss anything so that you get the maximum value out of this lecture. So now let's move to the OFDM simulation part. So we understand from the previous lectures that I gave about OFDM, two lectures were comprehensively focusing on OFDM, that OFDM is basically a transmission technique used to send your data in a spectrally efficient manner. And the way we are doing that, we are using the I50 at the transmitter and D50 at the receiver. So now we need to understand how to do that, how to execute this in a simulation environment. And as you know, if you can run it in simulation and make sure it works properly, you can take it to the hardware implementation. You just connect your Matlab code with a hardware device and send the code, compile it to C language. There is a compiler in Matlab where you can convert this to C, and it takes the code to the RF transmitter and just transmit whatever you design here on the air, real life. And this is going, so you basically, you don't learn only the theory, but also you know how to simulate, how to execute, how to build transmitters and receivers with hardware. And this is the ultimate goal, actually. But for us, since we are focused on producing novel algorithms, we will stop at simulation part, because if it works in simulation, we just need to push it to the hardware, and in the hardware, it's gonna work. There are some issues sometimes related to hardware impairments, channel calibration, but these are engineering issues. At the end of the day, a technician who's knowledgeable in these things can address and solve most of the issues related to the hardware implementation part. So the focus is going to be mainly on the OFDM part. So now when you open the Matlab codes related to OFDM, the library I shared with you, you will find two files. One file related to the book, and I assume most of you have gone and read specific parts of the book, especially chapter 3 related to OFDM, and there are other chapters related to MIMO. You can see how many chapters are here, but mostly if you are going to be an expert in OFDM, you need to go through this whole material in terms of channel, transmitter, receiver, integration, MIMO, all these topics. And there is another file that's related to describing the Matlab files. For example, you have a Matlab file called add CFO. It's carrier frequency offset to a given signal, how to add it. Add CP, how to add cyclic prefix. Add pilot, how to add pilot to estimate the channel. Symbol time offset, Alamotti coding scheme, if you want to integrate your code with Alamotti, if you want for WAM. So each abbreviation here has meaning, and this file is very important as it gives you an idea what this Matlab file is all about. So you know what's the purpose of this function, or what's the purpose of this Matlab code. For us right now, we will start from the most fundamental file and the most important one, which is the OFDM. We want to simulate OFDM, and when you extract the library here and put it in your folder, you will see the file named OFDM basic here. So you just drag and drop the file here, and you get it on the editor, on the Matlab editor. This is where you write the code and you try to execute and debug your simulation. So now when you open the Matlab code, you have the command clear all. We all know this. It means clear the workspace. The workspace is basically gives you, it stores the variables and their values. So any variable here you define in the Matlab, for example, NBPS equal to, once you define it and run the code, you will find it here. So basically this for saving the values of the variables you used in your Matlab editor. And this is very important, this workspace, because it enables you to debug the code and enables you to see the value inside that variable and how Matlab code changes it over time after each step. So it helps you debug. Now we will see how that can help us to debug our problem in running the code. And then after, there is also the command history. It shows you the commands that you have used on command window at specific times. So it helps you return back to some of the codes that you have used to execute. And here the command window. At this window, the results of the code appears, and also you can use this window for quick tests or for simple executions or simple code evaluation. For example, R equal 4 equal 3, and then you say X equal R plus C. So it's for just quick implementation, but for comprehensive long codes, you need to write M file here, where you can create a new script, where you can write your code or a new function, example, or a class like Java or object-oriented programming. And there are many other things, but actually, as you can see, I'm using Matlab. I'm using Matlab 2013. Okay, So it's not that recent, but it's still sufficient to me. I can still use it. I can run all the codes. I can do most of the functionalities that you might need or you might face. And most of the updates are incremental, so don't worry about the version. The most important thing to have just one Matlab code. But there is one issue with the versions. Sometimes when they update from one version to other, they remove some of the functions and release new ones. So the old, if you wrote a code using the old functions, the code will no longer run successfully with the new versions. To just fix this problem, it's super easy. You just need to replace that old function with the new function adopted by the new version of Matlab, and that's it. And that's the problem that most of you faced here. Yes, everybody can see the code here, the writing, or should I increase the font a little bit more? Yes. If the font is clear and there is no need to increase the size, I can go ahead. If you want me to increase it a little bit more, we can try to increase it more. So what do you think, guys? Is it fine? Is it okay? The font size.
Please increase the font.
Increase more?
Yeah. Yeah, increase more.
Okay, like this, for example, apply. Here, the code is good now?
Yeah, it's good now. It's good now.
Better, yes?
Yes, it's better.
So I think it's better to make it a little bit bigger. Okay, now you have this code. Everybody can see the code and we will follow it step by step. But before we follow it and most of the students, when they have this code OFDM basic, they just come here and run the code, yes? And as you can see, my Matlab version didn't give me any error. It just gives warning, yes? And I am stopping now. I'm stopping the simulation, Control C. I don't want to continue the simulation because it gives me this warning on rand int, yes? Yes, you got error in your Matlab version because you are using 2018, 2019. But for my Matlab version 2013, it was not an error. It didn't stop me from running the code. It just said, please take care of this rand int in line 41. Just click here, you go to the error, but not here. I don't want inside the function. I want it within my code, OFDM basic. It just, when you click, it just says that the error is basically in line number 40 in the OFDM basic.m. And the issue is with the rand int. This is an obsolete function and may be removed in the future. Please use rand I instead. Did you get this message? If you get this message, you must be able to figure it out. And even if you didn't, when you get rand int and gives you an error related to that, you must know that this is the issue. This function is old, is no longer supported. I need to replace it by a new function. It just says use rand I. So what I said here, I created, if I want to fix the problem in your file, I don't need to fix it here because it's just warning. The code runs smoothly. But if I want to fix it, I want first to open this X file. Yes, I open it. I go to the workspace here and I search for X. This is X. I click on it and open it. What's the content of X? 1, 3, 2, 0, 2, 3. As you can see, they are random integers from 0 to 3. They are related to Quam. Quam has 4 symbols and they are random integer from 0 to 3. So basically, I need to write a new function that can give me random integer. The output will be random integers and from 0 to 3. And the size of this, again, the size is basically n used multiplied by n frame. I see this, I can see that the size is 1 by 144. And I need to use the same. So what I can do, I can just comment this and write a new function, which is this. I just wrote it before the lecture starts. And instead of rand int, I'm using rand I now, as MATLAB instructed me to use. And I'm defining the range of values from 0 to 3. You can, I know now you might say, how did you know how to put these, how did you know you can put these values in this way? You just need to type help here on command window, help rand I don't know anything about right now. Could you please help me how to use it? Just to get all the material related to rand how to use it. And you see the examples, and from there you learn how to use it. And I just according to the examples, I write my function now related to my case. And I make sure that this one is the number of rows, and in used by n frame is the number of columns. So basically I want to have a vector, one vector line like this, and the size 1 multiplied by 144. So now can I run the simulator again? Let's run the simulator again and see whether it gives us an error or warning or anything red. Let's run it. Now it says that x here, undefined function or variable x. Yes, I defined this variable x, yes, and I'm using it here, but I removed x now. What should I do? I should rename this the same name, yes? So I run the MATLAB code again now. So it's now working successfully, no problems. Now it's running busy, and it gives me the bit error rate results and everything, and after that it will plot the bit error rate for me. Yes? Was it easy to fix this problem? Tell me. Simulation is finished and you get the bit error rate. Why most of you were stuck here? I don't know. If you are not patient, if you are not everybody among you has taken several courses in programming, isn't it? So if you face an error, red line, you just stop stuck, you don't work on it anymore. Learn. Try to ask Google. Ask help from Matlab. Matlab has very comprehensive help directory. You don't need to go to Google. Just type help and the name of a function. Or there are thousands of examples. So, and the MATLAB code now is running without any errors, without anything. Now let's make sure that x, the new x I just defined here, is giving me exactly the same values. Is it giving me the same values? 0, 2, 1, 2, 3, this. Yes, all the values are from 0 to 3, and I am having the same size, which means I am on the safe side. This function, this new function I wrote here, is giving me exactly the same output of the previous function. That's old, not supported by MATLAB anymore. Is that clear? Is that what you want to do? Here we are. Now we fixed the problem now, and we know that the MATLAB code is running perfectly, smoothly, easily. Just one minute of work, just with a little bit of focus and following up the problem. I solved the problem that you were stuck in it for more than 2 weeks, which is shame. Now, let's go to the MATLAB code step by step and understand what these variables are. Clear all, we all understand. And then here you define variable ng type. This define ng type, it determines whether you want to use CB OFDM or ZB OFDM. And I told you one time the difference between CB and ZB. Most of the talk was about, as if you remember, was about OFDM CB. You have your OFDM symbol in time domain. After you take the IFFT, you get here, and you cut this part and you put it at the beginning, and this is CB OFDM. Yes, I call this CB. Is that right? So now there is also another implementation for OFDM which uses ZB. ZB basically you take this. This is the new OFDM. You take this is the OFDM. You don't add CB here. You don't cut this and put it here. You basically just leave this part zeros. Just it has the same length as the CB, but it just puts zeros here. It doesn't copy. Now here it doesn't care about circular convolution. But what's the difference here? You need to change the receiver design. At the receiver design, now when you send this over through the channel, the ZB OFDM, when you send it through the channel, what happens to the OFDM after the channel if the channel has exponentially decaying function? The OFDM at the output will be something like this. Yes, this is the output after the channel. Now what you need to do at the receiver, you need to cut this at the ZB part, cut it, just take this part, cut it, and add it to the beginning here to compensate for the loss here and make the data circular. And this as if you are adding CB, but there was CB at the transmitter. Here as if you are cutting the part and putting it at the beginning and to make it circular convolution. And if it's circular, now you can use FFT at the transmitter, at the receiver side. Okay, these explanations are just for this line. Now since I'm using 1, I'm putting 1 here. This means that if NG type is 1, NT is CB. If it is else if it is 2, then ZB. I'm typing it 1, then it's CB. Great. Then we have another variable, Ch equal 1. If Ch equal 0, then please don't simulate over fading channel, simulate over additive white Gaussian noise channel. And the target number of error bit that you need to calculate before you plot the bit error rate is 100. You need to reach 100 errors in the 100 number of bit errors so that you say this is the reliable performance. You know, in statistics, you have to send enough, you have to take sufficient number of samples to say my result is this, my probability is this. You cannot say, but you cannot run the dice, for example, once and you see the value on the face 1 and you say it's 1, it's always 1. You cannot say this. You have to run the dice enough number of times, you have to make enough number of events and record the probability, and then when I ask you what's the probability of seeing 1, you say 1 over the number of all faces, because it's uniform distribution, all of them, they have the same probability of appearing, and you say 1 over 6. And here the same, we are sending thousands of symbols and we are seeing different number of channels. We need to cover all the different statistics of the channel. We cannot see all the different statistics in just one run. We need to execute and run the Matlab code for several times to make sure that we cover all the statistics, and then we say this is reliable results. For our case, we are using what? We are using channel, really fading channel. We don't want additive white Gaussian noise because it doesn't include the reflection due to building and due to cars and the trees and multi-path fading and dispersion and scattering. We need realistic channel, wireless channel. That's why we use we consider Ch equal 1, and when the Matlab code here checks Ch equal 0, it's not 0, it's 1, then you go to else and execute else, and then you basically choose the really fading channel. And in this case you basically have what? You need the number of errors you need to take in order to take sufficient statistics. We increase them to 500 because in really basically you have another source of randomness. Not only the noise, you have the randomness due to the channel, and you need to a little bit increase the number the number called target NEB, so that you get reliable statistics. Then we have a small definition here, figure, for to plot your figure uh, 2, figure 1, whatever. This is not important. Now after that, you come and define your channel, the one that you will transmit your data over it. Usually when we are simulating OFDM, we simulate it over a frequency selective channel. Frequency selective channel means time dispersive channel. Time dispersive, it has this characteristics, exponentially decaying. Why is that? Because in OFDM, the main goal of using OFDM is to send and transmit large number of data, very quick, fast number of bits, or basically increase the data rate. And this is the problem why we needed OFDM. You basically need to increase the speed of your internet, the speed of your data transfer. And when you increase the speed, the pulse duration shrinks, yes? It basically shrinks, and when it shrinks, basically the bandwidth increases, and since the bandwidth of the symbol now is greater than the bandwidth of the channel, the coherence time of the channel, you get frequency selective channel, and this frequency selective in frequency, in time, we call it time dispersive. So that's why it's realistic and makes sense to always simulate OFDM over a frequency selective fading channel if you don't have too much mobility. Clear why we consider why we didn't choose additive wide Gaussian noise? We are choosing this case because of this reason. Now you define the power delay profile, and the definition, there are many standard ways of defining it, but in this code we are defining it in dB, and we say the first tab that we receive, the channel has how many tabs with power? 5 tabs. 1, 2, 3. Yes, let's say this is our channel. This is the channel. First tab, second tab, then third tab. So this is basically our channel. When you can draw it, it's kind of exponentially decaying. So this is coming direct line of sight maybe, or this comes after reflecting of building, reflecting of maybe tree, reflecting of floor, reflecting of mountain. Yes, each one gives us a copy of the signal, another version of the signal, and this is how the channel behaves. And here it gives us the delay. This is the power value. Now you might say this is 0. How come you are putting certain amplitude for 0? 0 means no power. No, I tell you this is 0 in dB. 0 in dB, remember with me, the dB equation. dB is equal to anything 10 log the power in linear form. So basically, if you have 0 dB, 0 over 10, you divide over 10, 0, 0, yes? Now 10 to power 0 is equal 1. So 0 dB here, 1 watt. You understand me? And minus 8 is something less than this, and minus 25 is least. You understand this point clearly? And then you have the delay here. What's the delay? The delay is basically the time duration between the tabs of the channel. For example, the first one comes at 0 time, let's say, and the second one, with respect to the first, what's the distance? 3, let's say 3 nanosecond. And this 3 nanosecond, we just map it in our simulation to sample duration. We are simulating in terms of samples. So we say the spacing between them is equal to the spacing between 3 samples based on our sampling time and sampling frequency. And then the third one comes at 5 nanosecond. It's here. And the third at 6, and then at 8. So as you can see, the spacing between them is not uniform, which is normal. Then you have the power. We want to calculate the power of these all tabs, channel tab power profile, and since they are in dB, we want to get it in linear, because in our simulation, yes, although we are defining in dB, but in our simulation we need to use it in linear form. So 10, the power here, the power over 10, yes, the power, this is vector. You divide it over 10 from this equation. The vector, you divide it over 10, and then you take the log, 10 to power, 10 to power this, 10 to power t over 10, you get the power in linear form. And then you just calculate number of tab, length power dp, length, this function, MATLAB gives you the length, and then you define LCH, which is the delay end plus 1 channel length. This is channel length, this is channel tab number, and you are done with the channel now. These are the parameters you need to take care of when you are defining the channel. This is the channel we are simulating over it. It's given to you. You just need to use it in your simulator. But now you understand it. You understand the meaning. If you want to say that I have another channel, here where I can define the channel, here where I can change the channel. If you have millimeter wave channel, you need to change this to evaluate your scheme over that channel. Now you come to the to define the modulation, the mapping process. Are you using BBSK or QBSK? The carriers, the OFDM carriers, are they carrying QAM symbols or BBSK symbols or 16 QAM or what? You define them here. You define number of bits per symbol. If the number of bits per symbol is 2, then the modulation order is 4, because 2 to power 2, 4. And this means that you are using a QBSK or 4 QAM. Yeah, you know this from digital communication and wireless communication. After defining the modulation, so if you want to use BBSK, you just change 2 to 1. If you want to use 64 QAM, you just use log 2 64 is equal to 6. You just put here 6 and automatically adjusts. So now you understand this part as well, that it's responsible for modulation. And after that, you define the FFT size, the number of carriers that you have within your OFDM transmission. And the FFT size here 64, but it can be 108, 128, 512, 1048. You can define it the value you want. Depends on the number of carriers and the bandwidth you have. Because more number of subcarriers means more bandwidth. More bandwidth means you are buying enough spectrum from the government and you can generate IFFT size, assuming that the subcarrier spacing is fixed. More of this number means more bandwidth, more subcarriers. In LTE, for example, each subcarrier has 15 kilohertz. 15 multiplied by 64, it gives you the total bandwidth of your system. Okay, and then you have here, you define NG, the guard interval length. The guard interval length, you basically, this is not proper way of defining it. You define it basically based on the channel tabs. But here, when you divide the number 64 over 4, you get 16. 16, F16 is larger than the length of the channel, which is here 9. Yes, length of the channel, when you calculate here LJ, where is, let's see, where is it? Here in the variables. So you can see here the value of LJ is 9. Why is 9? You can see here only 5. Because we put zeros here between. If the number is not coming consecutively immediately after, if the delay here is missing, there is a spacing that you don't receive anything within it. But you can still, you have to count it as time. That's why since it's taking samples although I'm not receiving anything, but still waiting for the other samples. So you have the 0 tab, and then you have two numbers here missing between 0 and 3, and you have one number missing here. You don't have anything missing between these, and you have one missing here. When you calculate the total of these samples, you find it to be 9. So since this in G is equal to 16 and this is greater than 9, then you will not get inter-block interference between the OFDM symbols. You understand this point, yes? You have to make sure that the CB length, yes? Here your OFDM symbol, and this is the CB. The CB length here, from the beginning till the end, should be greater than the delay spread of the channel. Because we want, when the channel spreads, we want the spread to be contained within the CB duration of the OFDM symbol. We want, if it exceeds, it causes interference to the data. And if it causes interference, your bit error rate will not be good, and you will not be able to receive all the data successfully. So I believe this is also important point to mention and to take into account. So sometimes you might get errors. You don't know what's the problem. The problem might be because you are defining the CB length to be less than the duration, the delay spread of the channel. So what else we have? Now we come here, yes, and we define the values of the SNR that we want to define OFDM over. Yes, the values of we want to evaluate OFDM performance over 0 dB, 10 dB, 30 dB. But this is not like this. It's basically, this is the starting point, this is the end, and this is the step size. So this vector gives you 4 values, or 5, 0, 10, 20, 40, 30. Okay? Step size is 10. This is how you define it. And then now we define the number of iteration for the for loop. Now for loop, in each iteration we are sending random data and we are generating a new channel, and we want, why for loop? In order to get enough statistics for the channel and plot reliable bit error rate that does not change or fluctuate. And then you define the number of symbols in one frame. Yes, you basically in OFDM you don't transmit symbol by symbol. Yes, you just gather them together. Like this is the first OFDM symbol, and then this is the second OFDM symbol, and then this is the third OFDM symbol. You gather them together and then you send them within a frame all together. You don't send one by one, you just collect them. The minimum value you can use here, 1. You can select it to be 1. I want my frame to be only 1 OFDM. It can be. But like here, there are some practical issues related to that, but for this code, it's defined to be 3. And you define a variable called sig power. That's, you don't know that you will need it, but while you are coding the code, you will later discover and know why you need that. And then here you define file name. These are like extra things. You don't need to do them. File name, that please put the bit error rate in this file, and name it .data. Basically, it stores it here. You see this file? It stores the data that you get after you generate your bit error rate here. And then this, you define, you can also open the file and get the results and plot them. And here norms, this basically for normalizing the modulation order. So if you are using QPSK, you use this square root of 2 in order to make sure that the symbol power or energy is uniform. This is how we simulate. We make sure that the transmit power is uniform, is unity at the transmission side. Now, after doing all these things, now we go to the for loop simulation. For each signal to noise ratio value, EB in naught, take the EB in naught and evaluate over it. Then here you generate random integer. These random integer basically random data symbols, and they are drawn from QAM. And after that, basically these are the numbers, the integer numbers, and here you modulate them, QAM mod. You know what does this mean? When I showed you, when we opened X, we saw only values of, like, the values were 0, 1, 2, 3 for QAM, for QPSK or for QAM. This 0 means you are sending 0, 0 bits. 1 means sending 0, 1. 2 means sending 1, 0. 3 means this. Now this is binary representation. This is decimal representation. So they are basically the same, but I used another representation of the binary sequence. Okay? You understand now that this X, when you see 0 in it, this means that you are transmitting 0, 0. QAM symbol is carrying 0, 0. And when it's 1, 0, 1. And after that, you modulate it using this function, QAM mod. If I were you, I would not use this function. I would build the mapping myself. I will say that when 0, 0 comes, give this value to the, maybe to my symbol. When 0, 1 comes, give this value of that has this real value and this imaginary. When this value, basically, you can build a mapping table and map these values to complex number on the constellation diagram. But Matlab made this process very easy for us. It has a ready function. You just put your vector and the modulation order and divided by the normalization factor in order to make sure that it's unity, and then it gives us the result. So basically the input to this function, integer values that are representing the binary data here, and the output is what? Yes, what's the output? Let's see together what's the output. The output here, when you go, you can see it where here. X mod. I need to search for X mod. Yes, X mod is here. Open it. X mod, as you can see, complex values. And these complex values are coming from the constellation diagram. If it is 0, 0 here, let's say, you have vector of unity. If this is 1, if the value of this 1, why unity? Because I want to make sure that the power is normalized unity. I don't increase the power in order to simulate my system fairly and not get nonsense results. So if it is 0, 0, this is unity. If I ask you, get the X component and get the Y component, how do you get it? This angle is 45. 1 multiplied by cosine 45 is 1 over square root of 2. And since it's in negative direction, it's negative here. And the Y component, which is 1, the length of this multiplied by sine now, sine 45, gives you plus 1 over square root of 2. 1 over square root of 2 is 0.707. Clear? Do you understand these things? See, simple code, simple line of code, but it has all in it. There are all the information that I talked about in the lecture. So whether in digital communication or wireless or OFDM and 5G codes. So it's so important you get this. It's so important you follow the code. It's very critical you understand the in and out of each function. And it would be much, much better if you code the function yourself, because this shows that you are understanding things. And if your novel technique is related to modulation, you can contribute there. But if you are using a ready function, you are not going to be able to modulate or modify anything related to modulation. Yes? This is where, for example, my students, some of them are working. They don't want to use this function. They are building their own novel modulation function. So they are just removing this and building their own. Why? Because their contribution is related to modulation. If your contribution is related to modulation, you need to get rid of this and build your own modulator and make sure, and of course it has to make sense why I'm using this new modulator. It has to provide more advantages and some good merits that they are not available in the previous modulation scheme. Is this clear up until now? See the amount of information that each line of code has in it and the amount of knowledge you are getting by just going through one code. So now this is if statement to check if ng type is 2 or 1 to decide whether you are going to use CB or ZB. But here I believe I missed something here I didn't talk about. Here in NFT, this is the FFT size. And we understand in G, it's related to cyclic prefix duration. And the total N symbol is equal to NFFT size plus NG. This is the symbol duration including both cyclic prefix and the data. And we have NVC. NVC, virtual carrier. Virtual carrier, you know, when you modulate with IFFT, these virtual carriers, basically you don't transmit data over them. You just set them to 0, leave them empty basically. And the total number of OFDM carriers you are using, we call them in used. In used is equal to the NFFT size, which is 64, minus the number of subcarriers you left them empty. You left them 0 basically. You are not activating anything. Why do we do that? We do it for one critical purpose, which is reducing the out-of-band emission of OFDM. I talked about this problem while I was explaining. How does this happen? How does this work? Let's together draw the OFDM. You have, let's say, 64 subcarriers. Yes, you draw all of them. This. You continue 64. You have 64. Yes. If you take 64 and the other OFDM symbol adjacent to this OFDM symbol takes only 64, then you don't have any gap here. Basically, the OFDM, well, you are assigning this OFDM to user 1, and the next OFDM you are assigning maybe to another user 2. So basically, you will create interference, significant interference, because we know the sync oscillates. It has side loops. To reduce this interference, yes, well, what do I do? The subcarriers that are at the edges of the OFDM, I just cancel them. I don't activate them. So before you deactivate, your out of band is something like this. Let's say these are the power spectral density of the edge of your OFDM symbol. But when you deactivate some of these subcarriers, your out of band becomes something like this. The interference here, the edges, becomes lower. And then, since they are lower, you can put another OFDM symbol here in the frequency domain. But if they are high like this and put another OFDM symbol adjacent to it, you will get severe interference and your data will not be received successfully. Get it? Why we use in virtual carrier, and how many subcarriers we assign for that? 16, because 8 from the left, from the right side, and 8 from the left side, so that you reduce the interference. Now we reached here. Now these variables KK1, KK2, KK3, basically for assigning the symbols, the symbols you modulated here, the complex data symbols in the frequency domain, assign them to the location of the subcarriers. Some students, they may not need to do this at all. This is for practical purposes we are doing it here, but you can just map them directly. You can take this X mode and then add the CB to it, and then after that take the FFT. Where is the FFT? It's here. You basically, this is X shift. This is assigning a different position to make sure the zeros are at the edge, and you are not also, there is another important point, you cannot transmit over the subcarrier that has zero frequency, because this is DC value, and DC does not carry data. The data will not be transmitted over the air. So you must deactivate this. So there you put that value 0 at but if when you simulate here, of course you will receive it, but in practice I'm saying when you it doesn't go through the air. Basically this X shift here is just, as the name implies, you are shifting and manipulating and placing the data in proper places in the OFDM. After that, we are here in the frequency domain, in the spectrum. So you assign the carriers in the position you want and you like, based on the requirements and based on the practical usage of your application. Now, this is the critical important step. You take the IFFT, you move your signal from the frequency domain to the time domain, IFFT of X shift. So this is the frequency. Now when you take this X is time. And now you have your signal in time domain. After that, after you transform the signal to time, you add the CB. Yes, the guard interval. This was just for checking whether it's ZB or CB, but you don't add it here. You add it after you convert to the time domain, and then you do some other manipulations here that you don't need to do it for your simulator, but since it's already defined, you just stick with it. You don't, your contribution is not related to this, has nothing to do with that. You just, the important things are these. You don't need to play anything here because it's related to CB, and the channel values and the parameters here before your simulator. And after that, what do? You transmit over the channel. Now, one important point I want to draw your attention to is this. Now, as you can see, Matlab again made the process of taking or transforming the signal from frequency to time super easy for us. Just you say IFFT. But if your contribution is related to waveform building and the subcarrier shape itself and the spacing, you cannot use this ready MATLAB code IFFT to take the signal from frequency to time. You need to build your own transform matrix, which is, I am building it here. I build it here. This matrix shows you what's inside the IFFT. I build it mathematically here, and this enables you to see the sine and cosine and sinc. But with this, you can never see the sine and cosine and sinc with this, because the input is data, the output is data. Sine and sinc are not related to the data. Sine and sinc, they are the carriers. And where are they? They are embedded in this function. If you want to see them, you must not use the ready function by MATLAB. The same point that I mentioned regarding to QAM mode. So if this hides the technical details, the mathematical details, the knowledge from you. You just need to get rid of this if your contribution is related to building better waveforms with different shapes, with different subcarrier spacing, with different amplitude, whatsoever related to that. Now you will see the magic that we can do when we build the mathematical matrix of the I50 process by ourselves and see how you can convert the math to physics practically. But here I cannot see anything here. I'm dumbing here. I just no point of you just I50 input time input frequency vector output time done, and then you here add the guard interval, the CP. This is how you add it also. Guard interval, it uses this function. You don't need to use this function again. You can build your own. How do you build your own? You just need to copy the last part of this x, last part. Where is x? Let's open x together. X is small here. X is here. You need to cut this last part, last 16 symbol here from 48, from 48. These values, you copy them, and append them to the beginning. So how do you do that in MATLAB? You basically, instead of this, you can say my new X OFDM that has XCB, let's say, after CB is equal to X the data, and here X that I want to cut the last part of X, X1 49 till the end, which is 64, and then this basically connects the last part, takes the last part of X and put it at the beginning, and you append it to X. So basically the resulting vector is total X appended with this. So see how easy to do it without functions even, and makes your code faster. The less functions you use, the more time you will save in running your code, and the more you will be easily manipulate your code. So is it clear up until now? Now what remains now? You have your data in time domain, you added CB, and everything is going as we wish, and now we need to send it through the channel. So basically this is the channel. You define it, we define it again here based on the power delay profile that we have and based on the number of tabs. Since we are using multipath Rayleigh fading channel, the way to define multipath Rayleigh fading channel, since the real part of the Rayleigh fading channel is complex Gaussian, that's why you use rand-in. Rand-in is complex Gaussian function. You take random Gaussian variables from it. While rand-i that I used it for data takes the random data from uniform distribution function. And why? Because data should be, when you simulate your system should be independent of the data distribution, and the most random function, and that gives you equal probability for all the values to appear, is uniform distribution. So rand-i for uniform distribution, we got it, and rand-in for the channel, because the channel has different distribution for PDF. And for what's the length, how many data symbols I need, the length of the channel in tab, which is 9. This is for real, and this J for imaginary, and you take also 9, and you multiply this whole vector by square root of power over 2, so that each random value you generate here, it gets multiplied by its corresponding power delay profile value. Where is this in my code here? Channel, if you want to check it, you come here, channel, and this is channel, and these are the values. Now, these are the values without considering the spacing between them. To consider the spacing, you use h. This is h. Now, h is 9, And as you can see, at 2 we put 0, at 3 we put 0, because there is no multipath tab received at that point. And at 5, 0, 6 there is value, 7 there is value, 8 there is 0, and 9 there is value. And as you can see, real, they are real, this value real, and this value imaginary with I. From where these values are coming? From this function. Rand in, this brings you the real, and this brings you the imaginary, and they are taken from complex Gaussian distribution function. So now we move on, and we find you define the channel. Now this is the important step here. Now your channel is ready now, and you want to transmit your data over the channel. What happens when you transmit your data over the channel? A convolution, mathematically, the interaction between your data and channel represents convolution in math. And this, there is a ready function for that again by Matlab. However, if your contribution is related to the interaction between your data and channel, you must not use it. So with these functions, instead of writing a code of 1000 lines, we are writing a code of only 100 lines maybe. But as I told you, just if your contribution is not related to, for example, convolution, you just use convolution. However, if your contribution is related to this, you need to forget about using ready MATLAB functions and build your own function and adjust that function by your own way according to your idea to get better results. That's it. And then here you go over the symbols one by one, because the frame is composed of 3 symbols, and you do the convolution process and iteration and calculate the power. And after your data gets out of the channel, out of the convolution process, what do you get? You need to add, we get noise, we receive noise. We need to add proper value for we define a proper value for the noise and add it to our data. As the name implies, additive. It's additive, added to whatever signal you receive. The noise also is Gaussian distribution. You define it based on the signal to noise ratio. So basically, you determine what's the EB over N naught. Again, let's go to the math of EB N naught. Signal to noise ratio is equal to the signal power over noise power. Yes. Now this power, we understood that it's unity. We need to make sure that it's unity at the transmitter side. Yes, because we are not talking about the power to overcome now path loss. We assume that we are receiving with path loss. So now signal to noise ratio is basically, this is in linear. In dB, it's EB in naught. Yes, EB on in naught. This is the one we defined at the beginning, if you remember with me. Yes, we defined at the beginning here. You remember we said we are going to evaluate the performance of this system over these values, 0, 10, 20, 30. And here you come back, and we need to convert this from dB into linear, because in simulation, in MATLAB, in processing, practical processing, the value is measured in linear form. So basically, you do this operation 10 to power SNR over 10 and multiply by the signal power and take the square root, and you generate the random noise with the size, with equal size to the received data vector, and then you add the noise to your vector y here, which is this, the one that gets out of the channel, and here you say this is my received vector after noise. You don't need to play with this. You don't have anything to do with noise here. Just leave it as is, because mostly your contribution You can even, most of the contribution, you don't need to touch this unless you are maybe redefining the power, deactivating additional subcarriers, considering some other parameters. And here, again, resorting the OFDM subcarrier location, doing some shifts and the other things. But now, at the receiver side, what do you need now? You got your data. Yes, you got your data. The data is, there is noise added to the data. What's the first step then? The first step is to throw the CP, cut the CP, remove the CP. Yes. So here you come. This basically remove guard interval. This is the function that's responsible for removing. Of course, there is a function for that, but you don't need that function. You just need to cut the first part. You don't take it into account, the first part of the data. That's it. And then after you remove it, you take what? FFT. Now I am in the frequency domain, FFT. What do I need to do? I need to do frequency equalization. In frequency equalization, I am in the frequency domain. I need the data is in frequency. I need the channel also to be in frequency. So I have to find what's H in frequency domain. H also is equal to the Fourier transform FFT of H in time. The one I was showing to you, tabs and all these things, they are in time. You can take it to the frequency domain by taking the FFT of it, and then you get H. Clear? And then you make equalization. Now you get your data back. You are in the frequency domain. Now you have the complex data symbol, but you need to get the bits out of these symbols. They are carrying bits at the end of the day. I need these bits that represent my image or text or video or whatever. So you need to perform demodulation. QAM demod. Again, this is already functioned by Matlab. QAM demod, you modulate it, demodulate your data, and then you need to calculate the number of errors. I transmitted, let's say 1,000 bits and received 1,000 bits. How many of these bits are in error? I need to calculate this so that I can calculate my bit error rate. Yes, what's the bit error rate? The bit error rate is equal to the number. The bit error rate is equal to the number of bits that I receive in error over the total number of bits I receive. This is the bit error rate. And how the NEB is the number of bits in error. Some dB, you receive this vector, you transmitted this vector, compare between them, x transmit, x receive, and see how many of these bits are not matching with each other. There are many mathematical tricks to do that. You don't need to use this function. There are hundreds, thousands of ways to do it. And then you calculate the total number of bits you transmitted, and then if the number of errors, total number of errors that you calculated so far is greater than the target, break the loop and end the simulation and go out of the loop, so that I go to the calculation of the bit error rate. And then here you calculate the bit error rate. Bit error rate is equal to the total number of bits in error over total number of transmitted bits, and then you define some functions for the files and others, and at the end of the day you plot your bit error rate. You don't need to use these, you can use your own. You just I could have used this, plot bit error rate. Now for bit error rate and the in-note EB function, this will give me the plot. But in bit error rate, since the values are really in very low, usually we are talking about 10 to minus 3, 10 to minus 4, 10 to minus 5, which means one error in 10,000 bits you transmit. This is how reliable your system should be. We use something called semi-logging, function called semi-logging instead of plot. Now, this is what OFDM simulation looks like, and if you followed up with me now, I can you are going to be in a very good shape. You are going to be very comfortable with simulating your own idea related to OFDM, and now you simulate with knowledge. Now you understand what are you doing, you understand what these functions, what these lines relate to. You remember in the theoretical lecture we were talking about CB, OFDM, this, that. But now implementation, execution, now simulation, how to do it in practice. I told you this is also very compatible with the hardware. You just push it to the hardware, and you will be transmitting an OFDM signal over the air. But now let's stick to the simulation and focus on bringing new ideas and the new ideas, new technologies, and new methods that can improve the overall transmission. Now, the question we have now is here. Now, let's say now you are expert in OFDM simulation, you know the tricks, you know the ins and outs, and you are very comfortable. You know what to do when you see OFDM code. You know what each line of code means, and there is no worries, no fears when you see Matlab code. Now let's see if you can do this job now. This is related to 5G numerology, OFDM with different subcarrier spacing. So the question says, this is midterm exam question. Yes, it says the following. According to the current 5G standard, to minimize the interference between two frequency multiplexed OFDM numerology, I'm talking about this. You have one OFDM symbol with subcarrier spacing, let's say 15 kilohertz, and another OFDM symbol with subcarrier spacing of 30. This is for low latency, this is for high data rate. This is the scenario I'm talking about. To minimize the interference between two frequency multiplexed OFDM symbols with different numerology, enough guard bands must be used between different numerologies. You must make enough guard band. This is basically the guard band, 3 delta F1. This is how 5G is handling this technology, this interference. This is how things are standardized in the 3GPP. This is how Ericsson, Huawei, Nokia, Qualcomm, all these companies agreed to do. Yes? And I told you that this causes wastage to the spectrum. Now, however, I'm saying, however, this approach leads to a large waste of spectrum and thus increasing the cost of deploying 5G wireless technology. Because I told you yesterday in the lecture, spectrum is so expensive. People in 2015 they sold 65 megahertz for $5 billion or more. 10 billion. I don't know how much the value exactly, but it's very precious. So, and you are always sending OFDM. Everything in your system, in your network is using OFDM and sending. So little from this user, little from that, little from this Internet of Things device, it accumulates. It makes megahertz wastage. Megahertz wastage means billion of dollar wastage. So if you can come up with a little better technique to improve this, you are saving lots of money. You are making innovation, invention, coming up with a technique that can really save lots of resources. So this approach leads to a large waste of spectrum and thus increasing the cost of deploying 5G wireless technology, especially for the future scenario of massive device connections. Now, to find a solution better than the one employed in the 5G standard, the design of an effective approach method is required to more effectively minimize the interference between different multiplexed numerologies without sacrificing the spectrum nor losing the orthogonality between the subcarriers. Particularly in this test, you are required to design a practical, efficient approach that can minimize the interference between two frequency multiplexed OFDM symbols with different numerologies. You consider only 2 if you want, or 3, like the one I showed you in the lecture. But let's stick with 2 for now. And the goal is to come up with a different approach. Don't use guard bands. Come up with a different method that can reduce the guard band or eliminate it to minimize this interference and to save the world billions of dollars. And nobody has done the few research is going around this, and there is little information about that. You just use your intellect and knowledge and mind and the things you know and the MATLAB expertise you have to do that. And I will guide you how to do that. So where the first numerology, we assume the first numerology to have a subcarrier spacing of 15 kilohertz, whereas the other numerology has a subcarrier spacing of 30 kilohertz, as shown in the figure below. So basically, this is the question. Now, the first thing that might come to your mind, okay, now I understand. I just learned OFDM simulation, and I know how to simulate OFDM, but I noticed while we were simulating OFDM, we didn't see these subcarriers. Where can I see them? Where can I play with them? How can I create them? You cannot just plot them. You cannot just say, I'm gonna plot, I'm gonna draw by my hand, draw by a tool, or draw by Matlab, plot sync. Oh, get it. No, you must get it mathematically from the foundation of the I50. You understand me? So if you can reach that level, now you can have an idea of how to solve this problem. But in the code we just mentioned, we cannot see this. We cannot. Where is the? We didn't see I50 structure. It was just ready Matlab function. So to get rid of this and to get our hands dirty and in the implementation process of the I50, we need to just deassemble of this I50 and see how it's built mathematically. So we go here, we go to the MATLAB code for generating the I50 and I50 matricing and drawing them in time and the frequency domain. This is the MATLAB code. So to build the I50 matrices, the ones who know math, the ones who are very expert in linear algebra, and they know very well signal and system, the way we build the I50 is you define the dimension n and k, and let's say we are 64, 64, and then you make this multiplication process to get the indices of the matrix multiplied with each other, of course, and then here you define omega. Omega is the frequency which is equal to the exponential. Yes, you remember I50 is basically exponential 2 power minus 2 pi over n, over the number of subcarriers. This is omega. And of course, FFT, you need to integrate both the indices of the matrix you created here in the function here to get the Fourier transform. So F here, F represents FFT, the matrix FFT, and Fn represents the inverse fast Fourier transform. The difference between omega and omega n is the fact we don't have minus. Because at the transmitter, what do you use? You use I50. I50 has no minus, which is omega n. At the receiver, you use FFT, which has minus. So you use omega. At the transmitter, Fn, at the receiver, F. So I want to see these figures. I want to see these plots, the sine and cosine, the carriers that carry my data, how to play with them, how to change their spacing, how to put them adjacent to each other by math. And so that my question is basically here, if you noticed, the idea that one of you might think of, one might say, okay, they are interfering with each other, and I can see that there is little interference coming to this point, to this point, to this point from these subcarriers. So one solution might be to calculate this amount of interference and to try to subtract it or add something auxiliary you introduce something to your system that when you put it with these waveforms, it can subtract the interference, or you change the shape of this waveform so that it can make sure no interference to the adjacent one. Many solutions, or you can use other different methods that can coexist peacefully, or superimpose them, whatever. The innovation is yours. Now we want to show you what you need in order to get your hand on the problem and to be able to make things around and to play with them. So now we define the I50 and D50 matrices. Now let's plot them. Let's for example, I want to see, yes, let's get this. Now let's clear all. I want to see these functions that we all see in books, and we never, MATLAB is not allowing us to see them because they are using I50 ready functions. So I'm now going to implement this. You can see here, evaluate selection, and what's this? This command, fig1, hold on, plot real f. This command plotted for me what? Guess what? The real value of the first of the I is equal 5, fifth column of the FFT matrix. You remember with me when I said the FFT matrix is something like this? This is FFT matrix. And there are columns here. We build it now by MATLAB. Showed you how to build it. These are columns. Each column is an orthogonal base, exponential basis function, and each column represents a carrier. But each column is complex number. Each column contains complex values. They have real and imaginary. I told you in the lecture, real gives you what? Gives you cosine, and imaginary gives you sine. So I want to see this sine and cosine that's coming from this vector that I built mathematically. So to do that, what do? I just take f. This is f. This is the matrix. Let's see, where is f? This is f. This is the matrix that I built mathematically, the I50, the fast Fourier transform. These are the numbers that are inside the I50 matrix, and as you can see, they are complex. These numbers, basically, each column here, each column is basically an orthogonal basis function, which is corresponding to the subcarrier sinc in frequency and sine or cosine in time. I want to see these, to play with them and understand how they work. So I said, let's say, assume that I want to see this column, the subcarrier of this column. To do that, in MATLAB, you can write it like this. You take the matrix F, you take all the columns, you take basically all the rows. This sign represents that you are taking all the rows, but for this only column, only. So it becomes like as if you are taking this whole vector only. And what do you want? I want to take the real part of it. So there is a function in MATLAB, real, and then plot it. I plot it. I got this. What's this? As you can see, it's cosine. Now, as I told you, as you increase the index of the subcarrier, the frequency increases. Let's see that whether this is true. I'm gonna plot for which column? For 6, let's see. And I'm gonna change the color to see it to black. And let's plot it. As you can see, there is another carrier here that appeared, but it's red. And this is the red. What's the difference between the blue and red? As you can see, red is faster, means the frequency is higher, and the blue is lower. Basically, this is the real value. Both of them are cosine. Let's see for let's see 64, last subcarrier, and put it green. Plot. Go. Here is the subcarrier. 64 has the lowest frequency, as if it appears here, but because of the symmetry of the I-15. Let's take it here, 31, and see what we get. So C31, you have this basis function. See how fast is it? So now I know I can do the same for the imaginary. Yes? You can say here another figure for imaginary, and instead of real, I'm taking the imaginary value. I want to see that this is what? Let's say this figure, and this is what? Sine. Now increase the same figure. I wanted to take the seventh subcarrier and plot it, but change the color blue to see it. And this is the subcarrier. Again sine. I want to take now the 31. This is the sine again, starts from 0. So now I know how these things come. Basically, when you draw the signal, you are seeing it physically. Yes, you draw it. This is the signals that are on the air. Now I can visualize them and see them and understand what this math is bringing me. Imagine these are coming from these values. Things that I just math, they are making sense. They are becoming the carriers. Now, what else I want to see? I want to see them in the frequency domain, because this is how they plot them for us. Yes, in the box and this. Usually we see them in the frequency domain. So basically here, let's run this code. What do? You take the FFT of the subcarrier you select, and you increase the sampling period. You oversample it to get the figure clear on the drawing. So let's run these things, and you get them here. See, these are the sync values. You saw. Have you ever seen them in the book, in the presentation? You always see them. Some people, they draw them. They just say sync and this, but no, you must a better way of understanding how they come. You must get them from the FFT matrix, the I-15 matrix. So basically this, as if this a starting point for your for the solution of that problem that I showed you. You now draw, this shows you the drawing of two subcarriers, one blue and one green, and you are basically which one has larger subcarrier spacing? This. So you can assume this is 30 kilohertz, and this is 15. So when you put enough spacing between them, I was able to put them with no interference to each other if I place them with this distance. But this distance, I want to reduce it. I don't want this to happen, just because this is wastage. And this is the drawing of these signals in terms of amplitude. That was power. This is amplitude, how they go. Yes? Can you see with me the figures? They are so nice. I mean, now we get them, we see them. Not only play with them, not only we talk about them. So this basically, this code also, if you want it, I can also share it with you if you are going to be just committed to solve this problem. you are not committed to solve this problem, let's give you some assignments and homework, normal one, to make yourself busy with and just waste your time. Who wants this? Who wants to waste his time with just homework and assignment just to show me that you are delivering homeworks? Or you want to be committed and solve problems like the one I showed you and get the code that I explained here? So I assume everybody wants to be committed. Unless you have something else to say, please write it on the chat so that I can know and prepare the assignments and homeworks instead of focusing on your project and innovation and bringing new value to the market. Yes, guys. So I believe everybody wants to do good things. I hope everybody is going to invent something out of this class. Now let's go to the after you invent, after you come up with a solution. Now this is one idea. The other idea is to get in touch with your friend Muhammad Abawa and learn from him about non-coherent, the new modulation scheme called non-coherent OFDM subcarrier power modulation for low complexity and high throughput. He's right now writing this journal paper that now it's more than 30 pages, around 30 pages, and he's expert in this domain right now. This is basically a 2B project got funded out of the results of undergrad students during their work with me on the digital communication course. The project that they did in that course, we came up with a novel modulation scheme. We wrote 2 conference papers, got accepted, and wrote journal paper. And then we said, why don't we report this paper to Tubitech to get more funding to do more work on it. So basically, undergrad students, they were able to do that. And we got even money to work more on it and to assign more resources. So what this modulation scheme is all about, and you imagine, this is course project. This is not thesis. This is not something that was, but just imagine with me the capabilities if you believe in yourself and you just get in touch with me and make sure that you are synchronized and working on a novel idea. This is just this is the blessing. This is the barakat, as we say, as we know. This is coming out of a course project. You are taking exams, midterm, final, and along the way you are working on a novel algorithm, state of the art, and bringing something new to the market, something new to the 6G and 5G that nobody has even thought about. So let's talk about this modulation scheme. What's the big deal about this? What's the new contribution that all my students did in this, the undergrad and the ones who are following up? This, we said, like, in conventional frequency division multiplexing, which is the one was used in 2G and the many other previous technology, you were putting the subcarriers. Think of this like sync, but it can be anything. But for simplicity, we draw it in this way. Yes, you are with me, guys? So here, as you can see, you are you are separating the subcarriers by band, guard band, guard band, guard band, guard band. Lots of wastage for resources. Very bad design. In LTE 2010, we came up with the OFDM, became very popular, and they used it for LTE. And the key idea of OFDM is let the subcarrier squeeze them to each other, let them overlap, but they can still be orthogonal to each other. And due to this novel design, you saved bandwidth. How much of the bandwidth you saved? You saved half of the bandwidth required to be used by other modulation schemes. Now we said in the digital communication course, in the course project, we said, cannot we squeeze this bandwidth more? Cannot we save more resources? Cannot we do more than this? We said, well, let's think. If we combine it with modulation, and instead of assigning the data only, putting them to the subcarrier, why don't we manipulate and use the power of the subcarrier as another dimension to send extra data? And we came up with the idea of manipulating the power of the subcarriers in order to send additional amount of data bits. So basically each subcarrier, as you can see here, we have 8. To send 8 bits, we require 8 subcarriers. In this scheme, we send 4 bits by each subcarrier, 4 by each one, and another 4 by the level of the subcarrier. So basically both of them are sending 8, 8. But we send 8 while we are saving half of the bandwidth used for OFDM and 3 times of the bandwidth used by frequency this module FDM. And not only this, we are saving the power. Here you are using power. Here we are saving that power. Here you need more resources, and this corresponds to more time. Here we are less time. Here you need I50 size of larger size. Here you need I50 size small, not large, which means that you reduce the complexity significantly. Yes? So basically, we up until now, this is the 3rd journal paper related to that topic. This is non-coherent. We want the scheme to be able to work for Internet of Things devices without estimating the channel. So this is the basic structure of the scheme. This is the transmitter design, the receiver design. This is with MRC, maximum ratio. See the figures. When you write a paper, when you decide to become an inventor or researcher or creator or producer or contributor, making something new and of value to the community, you must not learn just how to read papers and how to. You need to be a good writer, good author, good programmer, good mathematician, good artist, and you have to at least get 5 to 7 skills simultaneously running with each other. So basically, we can give you the Matlab codes if you are going to be committed. I'm saying we will share only if you are going to be committed to do something great. We can share the Matlab codes of this and give you some ideas related to extending this to more communication schemes and more communication designs. So this is the simulation results that we got so far for bit error rate, for throughput, for without maximum ratio combining and with maximum ratio combining, and see the quality. They are not cut and paste from the software, low quality figures that do not look attractive. They are original. You just take them and embed them using latex inside your latex editor, and you make them of high quality, look like a scientific document. Not copy paste and I just want to get rid of my project and finish it as soon as possible. And here the peak to average power ratio and the other thing. So we need something of this value, something of this high quality. We just don't need people who are just want to do things no matter how it comes. You just do it and finish and get A and run out. Yeah, let's see whether this will benefit you in your future. Let's see. Now this work, we patented the idea in Lucy.io, and the problem with we patented it after we publish it. I don't know whether they will accept or not, because the thing is that if you have a novel idea and first you patent, then you publish. But we say that it is within 1 year. I don't know whether they allow it or not, but anyway, we are in this course. We are going to do first patenting if your idea is good and we got the results we expected, and then publishing, writing journals on this. And this, even if you don't finish it within this semester, finish it when you graduate, when you go home, when you go and build your own company. It's up to you. But I'm teaching you to be something who creates, something who produces. So, I mean, not only just copy paste and do low quality work and get along with it and just finish and there is nothing in life better than hard work and good work that you can produce and you can be proud of. So please take care of this and make sure you take things seriously and produce something of significant value in this course. So basically this is the form that I want you to fill before you start writing the paper or this. This form was provided by Nokia. Also, if you want, you can share your idea with Nokia. They might give you, like, they might buy your innovation, but they buy it for little usually, just $10,000. Not worth your efforts. If it's a novel idea that saves billion of dollars or million, why should you sell it or just get along with $10,000 for something that's really of value, significant value? So basically, you come here, you define field of technology and background of the invention you are doing. You talk a little bit, a few sentences about that. The problem you are handling, describe it, and then the prior art related to it, and then the invention you are providing, the technical implementation, basically how you design the transmitter and receiver. You mention the advantages and disadvantages. You put your simulation figures and results and any other supporting material you need to put. So this form, I'm going to share it with you guys so that everybody prepares his innovation based on that. And this is PDF form related to that, another form. I believe we covered all the things we wanted to talk about. Yes, guys? So with this, I strongly recommend you to go if you want to increase and strengthen your knowledge in OFDM, go through the book and what you need only. You don't need to read libraries. You don't need to, just put a goal. I want to do this. I want to be able to solve this problem. And whatever it takes from you to learn anything, study anything, to reach that goal, you will always feel motivated. You don't feel that you are studying. You don't feel you are working when you are seeking to achieve a goal. But if you just randomly read and this without goal, then you won't feel motivated, and you will always say, "Oh, when I will finish, what this problematic problem I'm trying to solve." You won't feel motivated or excited. So always we want to make sure that we are doing something great so that we feel motivated. Otherwise, we lose our motivation. If we lose our motivation, we would not have any energy to do any great thing. And once you put goals, then you learn anything required to achieve that goal. You don't need to randomly read everything. No, I just read the thing that I need to achieve my goal. And in that way, you save time, you make the best use of your time, and you save your resources, and you increase your impact. So I believe this is what I wanted to talk about in this lecture, and I hope the lecture was useful, helpful, comprehensive, and insightful, giving like supplementing and complementing all the missing information regarding technicality and simulation and a practical implementation and the possible future applications. So thank you very much for your attention, and meet you in the next lecture.
Thank you.
Thank you too. If you have any questions, do you need any questions? Anything? You have anything to say? Any problems?
All is clear. Yeah.
How was the class? A little bit technical, not theoretical.
Yeah, but it was good at least to learn the code itself. That was good.
I hope it was good for the others as well, and I hope this motivates you to do great things, hopefully. And thank you very much for your attention, and I hope I was able to motivate you enough to do things I mentioned. Although that, like, I'm not sure why not all of the students were here today, but maybe they have some issues, they have some commitments to other things, but they actually the ones who asked for that. So anyway, thank you very much, and see you in the next class.
See you.
You too.